Okay. Today we are gonna actually finish the basic DSP theories, and I have to mention that this is just the first part of the DSP. In many universities it's just taught as a DSP 1 course in a complete semester, but the point is that they go more in details, and we actually skip from many things, many small ideas that maybe they're not that much useful in the case of practical implementations, but for your knowledge improvement and to know more in details about the systems and signals and so on, maybe you would better to refer to the books and the references that you have already got. But for our class, we actually don't need to know that much, deep knowledge about the DSP theory, basic theories. So we are going to finish the DSP basics in deterministic sense, by studying over the systems a bit for different types of the system that we think is important to know. Because in practical cases, I will give you an example that why such a thing is really important to know about the system. And then we talk about the filters and different structures for the filters. And then we go specifically to two types of the filters which you normally deal with when you are having some DSP project. You normally deal with these two types of the filters, which are called infinite impulse response, or IIR, and finite impulse response, or FIR filters. Just in the middle of the lectures, in the middle of the slides, I'll try to have some MATLAB examples, and I will put some MATLAB examples also in the website for your practicing. And today I will actually release the first, second, and the third all in the same paper. You'll get everything today, and you can have the solutions by the end of the March, or if you think that you need more, if I get any email from more than 5 students among these 28, if I get email more than 5, I will definitely extend the time for one more meeting, maybe one more session, or maybe more, depending on your requests. But it's easy, it's not that much time taken. And I think that it's a crash course in the middle of this 2 semesters, so probably except for those students who are doing some master thesis or bachelor thesis or a project, probably for the rest it's easier to concentrate on the course. Okay. What we had so far, except for the case of the Fourier series that is already taught in the course of signals and systems in your bachelor, we explained very briefly about the continuous time Fourier transform and discrete Fourier series, discrete Fourier transform, discrete time Fourier transform, and Z transform. And classification of the areas which any of these transforms are applicable are briefly shown in this slide. So if the signal is periodic, we know that the Fourier series works well for the continuous time signals, and if the signal is discrete, then discrete Fourier series or DFT, discrete Fourier transform, is something that you can use it. And we know that for DFT, the algorithm which we actually use is FFT algorithm. If the signal is aperiodic, then in the case of continuous time signal, we use the continuous time Fourier transform, CTFT. the omega in this case will vary between minus infinity to plus infinity. So it's a wide range of omega, or the frequency that we can have. And for the case of discrete time signals, we have the DTFT and the Z transform. Z transform mostly used for the systems, and DTFT mostly used for the signals. Even though they can be replaced, I mean, their application is not dedicated to the signals or the systems. They can be surrogate methods, surrogate transforms in each of these categories. In the case of the discrete time, so we have the omega, which varies between minus pi and 2 pi, minus pi and pi. So the entire band is 2 pi. And for the case of the Z transform, is actually a generalization of the DTFT, with one exception, that we need to add a kind of region of convergence, ROC, in order to say that the series of the Z transform is identifiable if we are in a region of convergence, ROC, which should be defined. So these are the entire transforms, frequency-based transforms, that we actually deal with in the course. But we should know that the entire transforms are not actually limited to these 4 or 5 transforms that we explained here. We have a lot of more transforms when we are in the Hilbert space for the signals. We have several other transforms, homomorphic transforms, Hartley transform, Hilbert transform, and many other transforms. But they depend on the application, so we don't need actually to go through all of them. Mostly the Fourier transforms is more prevalent in the research communities, because we need some frequency-based components or information to extract out of the signal or the system. So we already talked about the convolution. In signal and systems, normally when you say convolution, we mean the linear convolution. In DFT processing or DFT transform, when we talk about convolution, we normally mean circular convolution. Here is an example of the circular convolution. Even though the results for both of the cases, linear or circular convolution, actually performs the same. For example, if you have the time signals convolved circularly, which is a circle, and the sign of the convolution in the middle. In the DFT domain, the result is multiplication. And you remember from the linear convolution, it was the same for the continuous time signals. So we had T, XT, and HFT as a filter. Again, we had a linear convolution, not the circular one, but the result in the Fourier domain was exactly the same. It was a multiplication of the filter with the signal. But the way that they are convolved are quite different. So here, if, for example, we have x1 defined as such, and x2 like this, when we mean convolution, well, you already know from the continuous time signals that for the case of the convolution, one of the signal or a filter should be first symmetrically reversed in time, and then you start to multiply by shifting the filter, for example. You shift it and multiply it by the signal. Shift it, multiply it, and then sum up everything and put it for the sample. Here we also do the same thing, but we already know that everything should be done in a window. And that window is actually the size of the signal that we have. For example, here if you assign the signal to be the size of n, starting from 0 to n minus 1, which means the signal is by the size of n, then convolving these two signals, it means that first of all you have to reverse the signal in time. One of them should be reversed. For example, x2 of n should be reversed. You can assign, you can assume that it's a filter. But reversing of this means that you need to do everything reverse in a window of size n. What you do in the discrete time is that you keep the first one, which is actually in the origin, which is 0, And then you reverse everything inside that window. Inside the window means that the rest of the things should be mirrored, but from the end. So we are doing actually the mirror in the end. So it means that this value now is here. This value is here, and so on. So this one is actually here. That's the way that we mirror actually the signal in a circular shift, circular manner, and this is the way that we represent it in mathematical form. Then you start convolution. So you multiply this signal with the original signal x1 and you get the results. So for the first one, for example, if you multiply that, the only result is 1 times 1 and you will get 1. And these values are 0 and here are 1. If you multiply them, the result is 0. And this one is 0 and this one is 1, so the result is 0. The only thing that you get when there's no shifting, just the symmetric inverse is actually performed, is the result of 1. Okay? Now you have to perform shifting. So 1 minus n, 2 minus n, 3 minus n, and so on and so forth. As an example, 2 minus n in the window of n is represented here. So 2 minus n means that from the other side, we are actually pushing one of the samples inside. So this one is pushing from this side. And if you do it 2 times, this one goes here, but 2 of these n's actually come from the other side. So here 2 minus n is represented, but we start from 1 minus n. We know that if 1 minus n is done, then we have 2 of these samples, so 1 and 2. So here we have 2, here we have 1, here we have 2, if you have 2 shifting. If you make 3 shifting, we're getting 3. 4 shifting, we're getting 4. Until L minus 1, we are increasing. Until n minus 1, we are increasing. Afterwards, we start actually to extract out the values, and from the other side, 0 is actually forced to the second signal. So it means that again we're decreasing until we come to the end with the value of 0. So the result would be something like that. So the circular convolution of 2 rectangular windows would be a triangular window. And the size would be increased. In the case of the convolution, we know that the size will be increased. The size is now increased. Yes?
This is the same as convolving 2 box signals, right?
Yeah. Yeah. The same. You know, when I say something in one dimensional, it's quite the same as in 2-dimensional cases. The only thing is that when you have one extra dimension, your computation is a bit more expensive. That's all. The point is that normally those 2 directions are called orthogonal. When they are orthogonal, all the operations that you do in one direction is quite independent from the other one. Okay, let me bring you an example with MATLAB to see So here, for example, we have a signal xn. That's a discrete time signal defined from 0 to 64. with these values, you see that frequently you have ones and zeros, ones and zeros, ones and zeros. Okay? Then you have h of n, which is already defined just to be a window, simple window, starting from 1, ending to 16. So, if you perform the linear and the convolutional and the circular convolution with different sizes, with different window sizes, what we will get is like this. If we do the linear convolution, so the linear convolution of x of n, the linear convolution of, oh, okay, interesting. This time we will see the mouse pointer. So the linear convolution of x of n with h of n, which you already know from the signals and systems, will give us such kind of result. So we know that for this to obtain, what we have to do is you get the h of n, and this was the h of n, you reverse it in time, then you start multiplication with the x of n, shifting and multiplying, shifting, multiplying, shifting, multiplying, and you get the results. So here we see, for example, here we know that you know, here is the maximum gain is 1, and here also we have 1. The number of the active taps here for the h of n is, well, 16, and here the number of the active taps are only 5. Then you have 3 zeros, and again it continues like that. So in the best case, the maximum gain that we will get wouldn't be more than 10. That wouldn't be more than 10. You just calculate it on a piece of paper, you'll see that. So we see that by doing the linear convolution, means reversing in time and then shifting, multiplying and shifting, that's what we get in the linear convolution. If we do the circular convolution in the window of size 64, which is the size of the signal. Here you see that the size of signal is 64. If we perform the circular convolution between xn and h of n in a window with the size of 64, as I already explained in the slide, as I explained it here in the slide, what we get in the result is a constant for the entire window. But if you increase the size of the window, if you increase it to 128, then, or even from 79 onwards, so add the size of these two together, 16 and 70, so it becomes, or 64 with 16, it's almost close to 70. And here, just for a marginal, you know, certainty, it considers 79, but it doesn't matter. You can, if you know that the convolution, the size of the window in the convolution as a result would be the sum of the size of this one and this one. So from that point forward, it's actually the linear convolution is actually you can add the zeros because it's nothing more to add to that window. So if you take the size more than 79 or 128, so these are the extra values, but doesn't matter. We'll see that the linear convolution and the circular convolution, this is the linear convolution and this is the circular convolution, they get the same result. If not, the results are different. So linear convolution and circular convolution, they will get the same result if the size of the window that we are restricting ourselves, we're limiting ourselves to find the circular convolution, if the size is large enough, they will get the same result. If it's not large enough, then the results are quite different. Because circular convolution is actually, we can simulate it like we have a cylinder and we're doing everything around the cylinder. So if the perimeter of the cylinder is large enough, then the linear and the circular convolution, they get the same result. If not, it's just like you're overlapping from the other side. So you round it around the cylinder and then again overlapping from the other side. That's why the results, if the size of that window is not enough, the result is different. That was just an example for linear and circular convolution. Now the point is that in computer we normally use DFT or FFT. We already know that in order to work with the frequency response of a system or a signal in the computer, we need to have samples from DTFT, and the samples are actually taken using the algorithm of FFT. So computer or the MATLAB understands FFT. When you do the FFT or the DFT, then it means that signal and the filter, if they are multiplied in the frequency domain, it's corresponding to a circular convolution in the time domain, not the linear convolution in the time domain. Now the point is that how can we get the linear convolution correspondence of such kind of signals? So here is the algorithm that gives us how we can do the linear convolution from the circular convolution in the DFT world. So the way that we have to get to it, even though in piece of paper is much easier to have the linear convolution, but practically we have the circular convolution. So if you really need to know the linear convolution using the computer, you have to do this process to get the linear convolution results. And for that, you have the filter and the signal. If the filter, for example, has the length n and the signal has length m, you must actually make them with the same size, n plus m minus 1, by zero padding. After you do the zero padding, then you can simply multiply them, and you use the inverse of the DFT or inverse of FFT, and you get the linear convolution. So we already talked about changing the sampling rate by talking about two concepts of upsampling and downsampling. And we already studied how they can affect the spectrum of the signal. With downsampling, the spectrum is actually getting wider, and it's actually bringing up the danger of overlapping the consecutive patterns from the original period and the neighboring periods. And if that overlapping happens, it means aliasing. And if aliasing happens, it means losing of information. For the case of upsampling, is the other way. So the spectrum of the signal is actually compressed, so we have no danger of overlapping of the signals. The only thing that happens is that the resolution in the frequency you're losing actually. So you lose the resolution but not the information itself. Now the point is that I mentioned already that upsampling and downsampling by themselves, maybe they do not mean a lot, but they are used for the case of filtering in filter bank implementations. That's actually coming with the ideas of noble identities. These are the identities that are actually named for the scientists. It's called noble. And what does it mean? It means that if you have a signal x of n and you downsample this signal, you get a signal like xa of n. Then if you pass the result, this signal, to a filter which is called h of z, the system which is represented in the z domain, you will get something like ya of n. Now the point is that you can replace these two if you change it in this way. So if you give x of n and then for this filter, if you use this filter first, then you have to do this z to the power of m. It means that you need to have, for this h of z, you need to have between every two samples, every two taps of the filter, you need to have m-1 zeros added. So if you do m-1 zero padding and then do the downsampling, then the result of these two are identical. I think you got it. So here you have the filter which is called h of z. Assuming that the filter is like this. Assuming that this is the filter, how can we represent such a thing? So h of z is actually 1 plus, here you have 2 z minus 1 because you have 1 delay, then you have 0 times z minus 2, and then you have 1 times z minus 3 and minus 1 times z minus 4. This is h of z. Now if you make it h z, for example 2, if m equals to 2, what does it mean? It means that between every two you have to add 1 0. So this actually corresponds to such kind of signal. These are from the previous ones, but 1 0 is added in between. Okay? And it's so simple, just we can study it over this simple example. Assume the second line, the signal is given to such kind of filter, and then you're doing the downsampling. The result is the same. You're in the Z domain. The Z domain behaves just like the Fourier domain, multiplication. And it means that this system with that one, this downsampling will be multiplied.
Can you write down the function for this, like 1 plus 2z power minus 2?
The function for this one equals to 1 plus 2 times z minus 2, 3, 4, 5, 6, plus 1 times z minus 6 plus or minus 1 times z minus 8.
Oh yeah, so I can directly plug in and then draw this graph too. So,
yeah. So this is actually h z square, and this is h of z. These are the corresponding equations. That's the first. So the first block is actually the first noble identity. The second one is actually goes with the upsampling. So the second one says that if you have a filter h of z and then you take the upsampling, it's quite the same as first taking the upsampling and then changing the filter with like this, adding L-1 zeros in between.
it's actually m minus 1, right? M minus 1 zeros, right?
M minus 1. Here we added 1 0 even though m was 2. Okay? These are two noble identities. We take these two noble identities afterwards in the filter bank design, and we'll see that how it can affect the computational cost. It reduces from n squared time to n log n just by using these noble identities and up and down sampling. You can also figure out how such thing might happen, that if we use the upsampling and downsampling, how it might happen that the result will be the same as downsampling and upsampling with the same rates.
Should we do the filtering along with this?
You have to write down everything, the equations. Otherwise, you will not be able to get the result. So you have to write down everything in the frequency representations, mathematical form of the analytical form of the frequency representation. So you have to get the signal x of n, then take it to the frequency domain, the TFT, and see what happens if you do the upsampling by the range of m, get the result here, then downsample it by the range of n, and do the same thing for the right-hand side, and then check what should be the condition to have the same thing in the output. I will give you the answer, but you have to investigate by yourself. And the answer is if m and n are prime numbers with respect to each other. So for example, 2 and 3, and 3 and 2. Then such thing might happen. It's not that much important, it's just for if you want to, play a new game in mathematics, you can have such a thing. So the polyphase filtering, which actually comes in the filter bank design, uses these noble identities and the idea of up and down sampling. But we will go back to it later. I just explained a bit about what polyphase decomposition means in a very simple example. And then we will directly go through the next topic, which is actually the filter design. And in the afternoon, I'll come back to the systems again, talking about the minimum, non-minimum phase, maximum phase systems. And I'll explain a little bit more about the polyphase. So the only thing remains from the polyphase decomposition. So assume that this is the filter, h of n, which has the values of 1, 2, 3, 4, 5, and 6. That's the sequence. And assuming that m equals to 2 in downsampling in the first noble identity. Then the polyphase decomposition comes, if m equals to 2, the polyphase decomposition comes with the first polyphase component as 1, 3, and 5, and the second one with 2, 4, and 6. If m is equal to 3, then you have 1 and 4, 2 and 5, 3 and 6. That's called the polyphase decomposition in practice. How it really behaves in general term, and in the if you just want to study as an analytical form, we can explain it later, or because I think it's useless and waste of time, you can just refer to the book to see what generally happens. But that's the idea. What I explained here is just the idea, simple thing that you can learn from this slide. And in general, if the system is h of n, if you decompose, if you want to get h of n again, the entire process here is just an identity process. So whatever inside is actually doing nothing. But it's not like to do nothing. It simplifies the computation. So by going through this and using this kind of a structure, using the downsampling, upsampling, and changing the polyphase replacement with the up and down sampling, then we see that in the filter design, filter bank design, it will actually help us to have a faster implementation. Yes?
Okay, switch on the slide sheet.
Oh, sorry.
I think there is an option in a PowerPoint to show the pointer in the presentation. Maybe right click into the presentation or something like this.
Pen. You can see it now, huh? Okay. It just highlights. Well, we have to test it before the class, but yeah, it just destroys the slide, but doesn't have any advantage. Okay, no problem. What about the laser pointer? You got it. Great. So we have the laser pointer. So as I already mentioned, here if you have, for example, the h of z, you can write down the h of z, the filter, in this way. So instead of, you have the definition of h of z. So we know that h of z is, for example, some coefficients times the z minus n. But now, if you can define this structure, we can define actually, if we define this structure, then it would be useful to reduce the computational cost. So polyphase decimation system comes in the beginning in such structure. So you have the downsampling and then the polyphase filter. So you know already the polyphase. I gave you an example. For example, E0 in that 1, 2, 3, 4, 5, 6. If you have, for example, m equal to 3, it means that 1 and 4. And you have small filters here with the downsampling in the beginning. And that's the structure that you use. Then you use the second noble identity in the end by replacing the polyphase components of the filter and the upsampler here. But then based on the block diagram theories, we know that we don't need to have all of these upsamplers here inside the branches. We can just take one of them out of the branch. So we replace all of these with just one in the output. The same for the previous one. We can ignore all of these downsamples with one in the beginning. That's based on the theories that we know already from the block diagram structures or the Mason algorithm and so on. So we'll go back to that later because it's not the scope of the course at the moment. In the filter bank design, we'll come back actually to it. But let's talk about the filter design. About the filters, we have to know that the filters are one of the most applicable subjects that we can face with in the DSP theory. So for any case, we know that signals that we actually record by the sensors are not clean enough. There are so many frequencies have been corrupted by so many entities like the noise. Noise is a sample, but for example, in case of speech recordings, if you do the speech recording in an environment which is open, maybe the noise is the only thing that happens. If you record the speech in a closed area like this room, then you have some reverberation coming back from the original source. So you talk and then some part of your speech that belonged to maybe 10 milliseconds ago or 100, for example, milliseconds ago, they come back and they mix with the signal that you are talking instantaneously.
Depends on the acoustics.
That depends on the acoustics and the geometry of the room. And that's the corruptive effect. You have to somehow get rid of these corruptive effects. So noise, reverberation, or even interference. You have, for example, interferences. Some other people are talking at the same time. These are the things that you have to filter out in order to get the clean and enhanced signal. The first one is actually the noise. The most important one is the noise. And we know that the noise is normally originated from a different source than the real source that we are actually recording. For example, in this room, my speech is actually originated by me as an entity. But there are a lot of noises like the one that you can hear from the fan of the projector. Or if, for example, there are so many computers here actually on and running, you can hear the fan of the computers. If there is a system like the air conditioner working, that's also another noise being added. If the walls are not isolated enough with the environment, and if you're close to the street, then the cars passing by, they generate different types of noises. Even the magnets like the switching on and off, which you cannot see it actually, for the lamps, they actually create a magnetic noises. Maybe it's not something that you can hear, but that will somehow affect part of the spectrum. So you have to get rid of these noises. If you know exactly where the noise is, so if the frequency of the noise is clear, so you can put a filter in such a way that that part of the frequency should be ignored, and you just get the part of the signal which only belongs to the signal. In some cases, or in many cases, you don't know actually where exactly the noise occurs. Yes, please.
Stupid question. In this case, can't you just remove the noise based on amplitude? Because I can hear only you. These are like way less compared to what.
Well, it depends. It depends of the signal and the noise energy. So SNR is the most important measure in that sense. Even for the case of the image processing, you know, for example, you have an image, and this image belongs to 100 years ago. After a while, that picture is actually corrupted by so many effects. One of them, for example, it can be salt and pepper noise. Then you have an information, but it has been hidden behind a salt and pepper noise. So what you do is running an algorithm to enhance the signal, get rid of the noise, and to get something which is more understandable by the user. In my case, I'm talking loudly, so I'm not talking in a normal way. If I talk, for example, in a normal way or very slowly, then you might not hear that, and it's because of SNR. So signal to noise ratio. Whenever we have a noise anywhere, one of the most important measures that you have to mention is the amount of SNR. How much SNR we have. Normally for the people, if you have the SNR more than 20 dB, if the signal to noise ratio is more than 20 dB, you know already the scaling of dB is a logarithmic scaling. If it's more than 20 dB, you can ignore the noise. In telephony speaking, you know, old telephone speaking where you were using the twisted pair telephones. The maximum SNR available was 20 dB, and that was sufficient. I think for the mobile handsets, it's now 25 dB. For the broadcastings, for the radio broadcastings, it should be the same, almost the same. In many applications, that 20 dB is not available. So even getting 10 dB SNR is sufficient to understand it. So the whole story of the speech-to-text projects, which is called ASR systems, Automatic Speech Recognizer system, is how to understand the sequence of the words happening by the speaker's mouth using the lowest possible SNR that you have. For example, I'm working on something, a kind of data set. That data set is recorded in -3 dB. -3 dB, it means noise is twice as stronger as a source. And I have to actually, the noise is actually, signal is somehow drowned in the noise. And you are actually getting rid of the noise to get the signal. So we have such kind of conditions. Military projects, normally it's like that. Noise is stronger than a signal. There are so many strategies to actually deal with such kind of projects. Some of them belong to the enhancements. Some of them are the theories going, for example, in the case of spread spectrum. So the spread spectrum theory is something that you're trying actually to get the signal out of more stronger noise. And there are many things in that regard. So filtering is an unavoidable process that takes place everywhere in signal processing field. Now let's talk about the basics of the filtering. We have different types of filters. Generally speaking, we have these ideal filters as low pass filter, which means that the lower part of the spectrum, lower part of the frequency components are allowed to pass, while the higher part of the spectrum are not allowed to pass. So if the signal has some more information than, for example, here in this figure, omega c, which is the cutoff frequency, if the signal has some more information and the information is not limited to this frequency omega c and has something more, for example, if between omega c and pi, that information will be lost and there's no choice. You will lose that part of information to the cost of canceling the noise, for example, or canceling another source which is going to happen in this part of the spectrum. That's the low pass filtering, the ideal low pass filters. For the high pass filter, from, for example, cutoff frequency omega c onward until the highest possible frequency, which is pi, you want to get the information and to actually cancel all the information beforehand. And this is for band pass and band stop filters. We already know that ideal filter design is impossible. Why? The theory we already studied. Because the ideal filter is not a continuous function over the frequency, so implementation of such a thing is impossible because it's unstable. We cannot design a stable system that the frequency response of that having a function which is not continuous over the frequency. So we cannot design such a thing, but it can be used as a benchmark of how we can design a filter which is more close to these ideal filters. Okay? As we explained already, the low pass filter like this, which is a rectangular window, and for the real applications we normally have a symmetry. So this low pass filter, here you have a low pass filter with a cutoff frequency of omega c, corresponds to a sinc function in time. So in time, that's a sinc function. If you don't do any phase shift, so there is no phase shift, just like this, you have the sinc function and that's all. Now let's see if we have a delay in time, what you will get in the frequency. We already studied from the Fourier transform, DTFT, that delay corresponds to a phase shift. A phase shift which is equal to the number of the samples times the frequency. For every frequency you have, number of the samples times the frequency. That's the amount of phase shift that you will get. So this phase shift actually changes the phase. So it's a bad effect. So delay corresponds to the phase shift. It's a bad effect. But on the other hand, it's the minimum corruption that can happen. So still we say a warm welcome to that. So if the phase shift is just a linear phase shift over the frequency, that's acceptable for us. Here is linear, you see, phase is minus, the shift of the phase is minus omega nd. So it's a linear function over omega. Because it's a linear phase shift, still is acceptable for us. If it was a nonlinear phase shift, that would be so difficult. Why? Because when it's nonlinear, you're not able to correct it. If it's linear, then just by knowing that linearity, you can somehow devise an algorithm to actually correct the phase shift, this phase distortion, and make it back to the original case. Otherwise, if it's non-linear, then it would be very hard, and you have always a phase distortion in the signal. And changing the phase or distortion of the phase means distortion in the signal. In many algorithms like spectral subtraction that we'll see actually later, spectral subtraction both in the image processing and in speech processing, or the Winnell filter, both in both cases, speech and image, you have the phase distortion. And for the case of speech processing, the phase distortion can be easily understood by the user. That phase distortion actually creates a kind of musical noise. They call it the musical noise. So if you listen to the original source, and if you listen to the one with the phase distortion, you see a kind of such a thing. You can actually listen from the, you can hear it from the phase distorted signal.
Is it radio?
Sorry?
Radio? You can hear the noise that we hear.
Yes, we can hear it.
No, it's from like, is it from radio?
It's because of distortion, because phase is not consistently moving. So if you have a linear phase shift, you will not understand anything. But when you have a non-linear phase shift, then that phase shift, because you need to have a consistency in the phase. If there is no consistency in the phase and it's non-linearly changed, then the effect of that phase changing in nonlinear form, which in spectral subtraction and Winnell filter you can understand it just by listening, for example in speech case, then you'll understand this phase shift. Phase is not consistent with the amplitude. And there are signs, there are some measures that we can understand how much nonlinearity or the phase distortion we've got by the algorithm. The method, one of the measures is actually called group delay. So the group delay would be constant if you have a linear phase shift, which is actually the derivative, the first derivative of the phase. It's called group delay. If it's constant, it means that you have a linear phase shift. It's okay. It's not a problem. It's okay. It's not called as a distortion. But if it's not constant with frequency, it means that definitely you have a corruption in the effect of the such kind of phase shift, which is nonlinear, would be something that you can understand it. The quality would drop down. Designing of filters. There are methods of designing the filters. In general, we have IIR and FIR filters. What does it actually mean? Infinite impulse response and finite impulse response. So it means that the impulse response of such kind of filters are infinite or finite. If we have such kind of filter, which goes to infinity, even if it's damping down, the amplitude is actually damping down. What kind of filter is that? If that's your filter, what kind of filter is that? That's the envelope of the filter. Assume that this is the envelope of the filter. You have the taps, these are called taps also, filter tap. The taps of the filter continue until forever. So it's infinite impulse response filter. This is called IIR. And if it's limited in the size, for example, you have something like that. So everything is actually bounded in a window of size n, whatever size. Then it's called FIR filter. So people might say that this FIR filter looks easier, so why should we go to the IIR filter? The point is that the natural way of the filters are almost, or the natural way is always IIR. So if you're talking about, for example, the analog filters, those filters which are made by capacitors, resistors, and conductance, it's always IIR. You will not get, and there's no way to get a FIR filter for that. It's always like this. So the impulse response always goes to infinity. It's always. That's why, for example, if you use the anti-aliasing filter, that anti-aliasing filter should be devised in analog form, and definitely this response will be IIR. But that's the IIR filter. But these FIR filters are actually the privilege of using DSP theory. We never had such kind of filter. In analog form, we never had such kind of filter. These are the privilege of using DSP theory. And they have very nice properties. For IIR case, it's the stability of the filter, which is one of the problems always we deal with. So for IIR case, we always have the problem, and we have to study over whether the filter is stable or not. If the degree of the filter, the number of zeros and poles belonging to that filter, is it in such a way that the filter finally is stable or not? For FIR filters, we know that FIR filters are always stable. For IIR filters, we have no control of the phase. For the FIR filters, we are able to design FIR filters with the linear phase. We are able to design that. That's one of the advantages of using the DSP theory and doing many things, many telecommunication projects in DSP. So nowadays, there are many telecommunication projects that they are changing from the old circuit-based design into the DSP-based design. They're trying to do that. Because in DSP-based design, we have more control on many things. That was not possible in the case because of, ATD samplers, the limitations of the samplers, the limitations of memory, and so on. But nowadays, it's possible to have a large memory even inside a very small circuit. And you can have a very powerful CPU to do all of these processes just instantly, in real time. And the entire theory you can just look at in the Google by software radio. They call it as the software radio. Software radio is actually the concept of implementing all the telecommunication blocks, building blocks, using the software, DSP software. So implementing everything in a DSP. Doing the modulations, everything, the modulations, equalizations, training sequences, compressions, codings, encryptions, whatever algorithm that you have in the telecommunication systems, implementing everything as a software. And it's also very easy to change it. It's very flexible to change it. For example, if you have an analog circuit for example, you want to change the frequency of multiplication, the AM modulation or FSK or FM modulation, then everything should be done, using the elements. You have to change the capacitors, inductors, and so on. We're changing the design of the circuit, and it means that the design of the circuit should be done in advance. You have to care about many things. But when it's just a software, it doesn't matter. It's just using Using your computer, you change the frequency, you change the filters, you change whatever necessary for that, and then just re-implement it. Rerun it, you will get a new set. So that's why they say software radio or software design radio is DR. So FIR is just the privilege of using DSP theory. That's why we have two types. But why IIR filters are still used? Because they are in many cases still necessary. And in many cases, for example, if the filter size, you get something is in the universe, you will not get anything without losing something. It's a trade-off. So there's no free lunch, The story of there's no free lunch. So designing an IIR filter would be much simpler using many smaller tabs, or in general, much simpler. But the same, if you want to design an FIR filter, having the same applicability of that IIR filter corresponding to that, then the size of the filter will be much more than what you will have in the IIR. So the computational cost of FAR filters are much more than IIR filters. That's the trade-off. Cost of computation, and if you have a good CPU, good memory, that's not a problem. That's not a problem at all. If you have problems, then you have to make a trade-off between these two, which one to use. On the other hand, FIR filters will give you the linear phase. You will have a good understanding of the phase changes. You know that it's stable. Doesn't matter how much is the degree of the filter. You know that for every filter, in the analog case, we have degree. So you say that the degree of the filter is like this. For every pole, for example, for every degree, we have 45 degrees of changing the phase. And if it's going beyond 180 phase change, then it starts actually to become unstable. For the FIR case, there's no instability. It's not a problem. So these are the things belonging to the theory of the filter design. So on the other hand, we have already a very rich theory in the IIR case, designing IIR filters in the analog form. So if we can somehow leverage those theories in the analog case in the digital case, then it will actually simplify our whatever we want to do. That simplifies the task, designing the IIR filters. But for the FIR case, everything is just from the scratch. We have to kick off a new protocol how to design this kind of filters. That's why for the IIR case, we have two different approaches. One of the approaches is just design an analog equivalent and then take the samples out of that. And you will have an IIR filter in the digital case. And we already have a rich theory over analog filter design, like the Butterworth, Chebyshev, and so on. These are already in the analog form of the filters. And also we have a designing using the direct design by the computer. For the FIR case, we can do the windowing filter. So very much similar to the first approach of the IIR filter design, taking the samples using the windows. We'll explain it later. Or we have a bilinear transform, frequency sampling approach, or we have a computer-based approach. I will not go much in detail of all of these cases, just I will explain in a very short statements, or maybe one slide for each. And just bringing up one example out of that. Because finally we'll have a software in MATLAB that can design a filter pretty nice and will give us the filter tabs that you may need, for example, to implement in a DSP hardware. And nobody these days actually, as far as I know, goes and design these filters using the paper at hand. They just use the FDA tools to write down FDA tools, and then this, they just set up the parameters to get the filter that they want, and we will see later that it will just right away give you the filter tabs, and they just implement it. That's all. So we already explained about the attributes of those filters. So FIR filters are inherently stable. We have no problem of stability, and they are easy to implement, and they have linear phase, while for the IIR cases we don't have such properties. Systems of IIR filters are more general than the FIR filters. So if you need a system to be like ARMA systems, autoregressive and moving average altogether, or a system which contains both zeros and poles. So the transfer function of a system, if you want to have such kind of transfer function which contains both zeros and poles, like here. This is a filter containing zeros and poles, like this. So these are different types of representations of a filter. If this is HFZ, it can be written by the numerator over the denominator, and if you just factorize the numerator into zeros, so you have Z1, Z2 up to Zn zeros here, and you have P1, P2 up to Pn poles. And you already know from signals and systems that what zero and what pole means. Zero is actually zero the frequency, zero the signal. If you give a signal which has a frequency equal to the zero, that signal in the output will be vanished. On the other hand, if you give the signal which has a frequency which belongs to the poles, if you give it to the system like that, then the output will actually get to the highest point. It will be saturated or it will explode the device, depending on how the device is actually invented. So these are the zero and pole effects. And you have a constant gain, if the system has a gain. This kind of definition is the most complete definition of every system that you might have. It can also be represented like this. Just you take the first coefficient to be 1 as a constant, and then you normalize all the other coefficients with AK. It's not a problem. Then you apply such kind of filter to the input signal to get the output signal. What is the effect of such kind of complete system? The effect is like this. If you have a system containing both zeros and poles, the effect of that on the signal, input signal xn, is that we know that the system and signal, they convolve and they actually give the output as yn. If the system is this much complete, then the output would be something related to the input plus something related to the previous or the last versions of the output. So we have a feedback from output. There is something related to the output here. But if, for example, you don't have any zeros here, it's just 1. 1 over 1 plus something. Then what happens here? This term vanishes. So the output at the instant time, the time n, will not depend on the previous times of the output. You will not get any feedback from the output. Now you can tell me, if we have an FIR filter, which is all pole filter, do you have any feedback from the output? You won't. But if you have an IIR filter, you have feedback from output. And now you tell me, is feedback by a sense something good or bad?
Good.
Depends.
Improves stability, right?
Generally, is a good solution for many cases to have a feedback. So that's another trade-off, whether we have to use IIR filters or FIR filters.
FIR filters, they come actually with so many advantages. But on the other hand, you have no feedback from the output. Is that something good for your case or not? Depends.
Isn't it always good if I have some error and I don't give feedback, I just keep pushing these error over and over and over and then
That's why when we go further in the theory of DSP, other areas, we use the adaptive filters. They are FIR filters, but they are actually using least square error submission. So they get the error submitted to a system, and they start to calculate the least square error using this gradient descent algorithms or Newton algorithms. They try to minimize the error based on the case of the cost function or something, and still they use the FIR filters. While for the case of IIR filters, normally they have the feedback from the output. Here is clear. So if you have an IIR filter, we have the feedback from the output. We have it by a sense. But for FIR case, we don't, because it's output filter.
what is the disadvantage of feedback?
What is the use of feedback?
Disadvantage of feedback. Like you said, like might be not useful sometimes. So
Sometimes it might not be useful, but in many cases, if you have a control system, for the control systems, if there is a kind of actuator, and that actuator is actually bounded between an upper bound and a lower bound, and if it, for example, exceeds the lower bound or the upper bound, then something dangerous might happen. You have to control everything. The gain, for example, should be controlled. Have you heard about the PID controllers? Proportional, integrator, and the difference controllers. So PI and D. Those PID controllers are really, related to the output. You have to make a feedback. You have to to have a feedback in order to know that how much gain you should give to the system, or how the parameters of the D and I should change. In those cases, the feedback is something necessary. So, as I told you, we don't get the ideal filter. So that's why we have to approximate the ideal filter. Approximation of the filter comes like this. So you have a pass band. Here is called the pass band. The band which the signal is actually passed through. And you have a transition band. The band which signal actually transits from the highest, so not the signal, the system, actually the system performance goes from allowance to actually blocking the signal, and the stop band doesn't allow any signal to pass through from this frequency onward. These are the omega of the pass band, cutoff frequency, which is normally between the pass band and stop band, and the rest. And for the digital case, we know that the highest frequency is pi, minimum frequency is 0, and because it's a real implementation, so you have a symmetry, something exactly the same way in the other side of that. But we don't care about the other part. Whatever you design here, that would be symmetrically on the other side. The point is that for many cases, if you design, so you have some oscillations on the stop band and the pass band, and you will have different filters based on the degree of the filter, this steepness will differ. So you can have something very sharp or something very smoothly going from the pass band to the stop band. Depends on the degree of the filter. For the IIR filters, we never have gain. So in the analog design, the maximum is always bounded to 1. You will never exceed 1. In the digital IIR filter design, you can even have more than 1. You can have a gain. Even for the FIR design, you can have a gain. That's one of the other advantages of digital versus analog filter design. You can have a gain. So normally we have 1 if you want just the signal to pass through, and you have a margin that you allow that margin for the filter actually to oscillate between these two margins. And in general, we take those margins symmetric. So whatever you allow from the lower bound, the same size in the upper bound, you have a margin. The same margin you have for the pass or the stop band. So these are the parameters that you have. So all these parameters should be set if you want to design a filter. So the margin of the pass band, margin of the stop band, this stiffness, how much it should be, or somehow this distance between these two cutoff frequencies, stop and pass band. That's the design of amplitude response for a filter. What happens for the phase? In filter design, we don't care about the phase. IIR filters, we have no control of the phase. So the whole theory of filter design is about amplitude design. We don't care about the phase. In IIR case, we know that the phase changes wildly. We don't have any information about that. We can, if we know exactly what's the filter, we can just, calculate it by hand to say that, okay, the phase should be finally going to this. But how it changes, we don't know. In FIR case, we know that phase is linearly changed, that's all. And we select those kind of FIR filters which, we have some idea about the phase change and how it's done. So one of the design methods is impulse invariance method. As I told you, we know many things about how to design analog filters. Take one of those methods, and when you design the analog equivalent of the digital one, take the samples out of that. And that's the way it's mentioned. So you have the Laplace transform. You design the filter in the Laplace domain because it's analog domain. That's the Laplace domain. Inverse Laplace it. Whatever you get is in the continuous time. This filter in the continuous time, take the sample. You sample it. You take the sample, you have the digital one. And the entire theory that we had for the sampling. What happens in reality is that you're actually mapping the poles of the system that you had in the Laplace transform into such kind of system. Zk, which has this relation with the sk. So whatever sk you already got, here you have the poles e to the power of skt. And t is the frequency of sampling, period of sampling. So in the S plane, if you design a filter with such kind of zeros and poles, the mapping to the Z plane would be like this. Everything is actually mapping to the unit circle. Inside the unit circle, these are the zeros and these are the poles. The right hand side of imager and the real part of the set. That's how it works in practice. We have some options like the Butterworth low pass filter design. So for the Butterworth, the amplitude square is defined like this. 1 over 1 plus j omega. Omega is the frequency. We can change it from 0 to whatever. And the denominator is actually the cutoff frequency. You set the cutoff frequency to be something. For example, 1.2 kilohertz. And you want to ignore the rest of the frequency band. And it should be to the power of 2n, which n is the degree of the filter. So the more value you give to the n, it means that your filter is more complicated. And it means that more computation is necessary for every convolution of the signal and the filter. If you take the simpler filter, it's better, but probably you will not get exactly, because here you see that how it changes. The steepness or the sharpness of the filter depends on this n. The larger value for the n, it means that the sharper can be this pass transition band from the pass band to the stop band. It should be sharper. And it's much closer to the ideal case. On the other hand, you have more computational cost. And it's also getting closer to instability because it's IIR. That's the Butterworth. The Butterworth is also called maximally flat because based on this, you see that here in the pass band, it's completely flat. There is no fluctuation, no oscillation. So if it's necessary for your project, for your application, not to have any oscillation in the passband. There are some applications that they actually ask you, someone asks you, please design me a filter without any oscillation in the passband. If that's the requirement, then you can use the Butterworth. Because for the case of Chebyshev, we see that having the oscillation in the passband is actually unavoidable. You have always oscillations in the passband. Even though designing a Chebyshev filter gives you a more stable filter and simpler with lower degree of N. But on the other hand, you have this oscillation. So there's no free lunch. And the way that you actually go through this filter is using these cosine functions. And because of these cosines, you are having oscillations. There are rich theory of how to design this. We don't need to go through that. As an example, how do you go to the process of designing a filter? Somebody asks you, okay, try to design a filter which passes all the frequencies between 0 and 0.2 pi, so a fraction of pi over 5, passes with this margin. So everything should be at least this much gained, and at most with a gain of 1. That's the margin. And for the stop band, shouldn't increase more than this. That's the maximum allowance for the gain in the stop band. Almost, you can see that almost you have 10 times, so that the ratio is almost 10 times from the pass band to the stop band. Here maybe less. So the attenuation is almost 3 dB is equivalent to 2 times. So when you have 10 times, it's almost 6 dB or 7 dB. For example, 7 dB attenuation. 7 dB in many cases is not a good filter. So 20 dB is something that people need in many cases. At least 10 dB, 20 dB, 30 dB, that's a perfect filter. So knowing that, what we try to do is just go into the analog equivalent of that. So you go to the analog equivalent of this. You use, for example, one of the methods here. You have used the Butterworth filter, and using these margins, try to figure out how much N you should have. So we figure out the best N, putting all those margins. This constraint should be satisfied at the same time. So this value for the margin, this value for the passband margin, and the other margin, both with the same N. Then you come up with some N, but it should be an integer value. So what you do is you round it up. If it's, for example, 5 point something, you take 6. It means that from now on, the degree of the filter, we know that is 6. And you have already the cutoff frequency. These are the things that we already got. So N must be an integer. Then you get the SK values from the Laplace transform, and then you have the H of S, which is the filter in the analog domain, based on these poles as zeros. So you have all the poles here. And then you have to map it to the Z domain using e to the power of sk. So instead of any sk values, you just use e to the power of sk, and whatever you get is the filter in the Z domain. But actually you don't need to go through that. The software will do that for you all almost instantaneously. The second approach is bilinear transform. The bilinear transform has this idea that analog form of the frequency changing is from 0 to infinity. Then it tries to map the 0 to infinity to something bounded, not going to the infinity. And do we have any kind of mapping function that can do such a thing? Yes, we have the tangent inverse. tangent inverse is actually a function which can map something from 0 to infinity to something between 0 and 1, or minus 1 and 1. So using this kind of transform, which is called the bilinear transform, you will actually have any SK that you make, you can just replace that in the form of the Butterworth design, or the first way method of design. You have the e to the power of SK. Here you just use this. Instead of S, you can replace that, but with this bilinear transform. So any design that you made it using Butterworth or Chebyshev, the SK values should be replaced with this fraction. Then what you get is a bilinear transform. The only difference is that the filter, as a result of this kind of mapping, is frequency selective. So when I mean the frequency selective, it means that it just takes, part of the frequency, it jumps from one frequency to another. So for example, it works like this. So you have jumps in some places. Here you have omega C1, omega C2, omega C3, and so on. If you have such kind of a strategy to design a filter with different, it's not smooth like, for example, the first method, which is something like that, or for example, the high pass filter. So if you have something which is frequency selective with different levels, you can use this bilinear transform. And this is an example, the same example we had already, just by replacement of S with a new bilinear transform, you will get a new filter. About the FIR filter design, we already see that the h of z can be defined like this, h of n, z to the power of minus n. That's the definition of the transform for any kind of system. And now the system is gonna do filtering. So we have different methods to apply for the FIR filter. But we want also to take the advantage of the FIR filters. So we already saw that FIR filter can be designed in such a way that gives us linear phase shift. And that's really a good advantage. So how can we get to such kind of FIR filters? That's the story of designing the filter. So the filter, there's a theory that says if the filter is in the time domain looks like this, so we know that the filter actually is bounded in time. FIR is a finite impulse, so it means it's bounded in time. If it's bounded in time, for example, in a window with the size of n, here is the size of n. If you design the time domain window, the time domain filter in such a way that h of n equals to plus or minus of h of n minus n, then the phase shift, the argument of the phase shift of the filter would be a linear, would have a linear function with respect to omega. And that's what we really want. If you want to skip from nonlinear phase shift or distortion in the phase, take this form and definitely you will have such kind of phase relation. So the phase of the system has a linear relation with omega. And that's what we want. So the same things that we had for the IIR case, we have for the FIR case. Let's go to this slide. So if you want to have a linear phase FIR filter, which we have, we need actually, that's a requirement we need. What we really do is that we have these four types of definitions in the time domain that can finally result to what we need as a linear phase shift. So if you take it like this, then it's called, if the number of the coefficients would be odd or even, and this is the equivalent h of omega. That's the equivalent frequency response. And these are called type 1, 2, 3, and 4. What's actually the difference is that, for example, for the first row, the type 1, what you have is that the filter in the time domain is in such a way that there is a symmetry at point m, for example here, assuming that this is your filter, assume that this is your filter, then there is a symmetry in the filter at point m half. So you see that the left hand side and the right hand side are quite the same. Well, no, it's the same. So if the filter is like this and the point of m half also belongs to the filter, it's called type 1. Type 1 FIR filter has the structure like this. So you have a filter with size, for example, n, and m half is a point which belongs to the filter, and if you put a line there, right and left hand side are mirrors. That's called the type 1 filter. If they are not even mirrors, but odd mirrors, then it's called type 2 filter. So, for example, assume that the second part is like this. They are odd symmetric, not the even symmetric. Then it's called type 2 filter. If it's even symmetric, but the point m half doesn't belong to the filter, so it's a gap. It's actually a virtual point. There's not such a kind of point for the filter. It's called type 3 filter. And if m half doesn't belong to the filter and you have an odd symmetry between the left and right hand side, then it's called type 4 filter. And the length of the filter can be anything, depending on n. These are the 4 types that are written here. I'll briefly explaining this like that. So that m is something that defines the point of symmetry. N, capital N, is something that defines the size. So, or here is actually, we replace actually. So here, m is actually the size of the filter, which is n. And m half is the point which belongs to the filter or doesn't belong to the filter. And you have these 4 types of the filter: odd symmetry, even symmetry, type 1, 2, 3, and 4. So here everything briefly is explained. Type 1, 2, and 3, and 4. N should be even, here should be odd. If you want to have the point belonging to the system, it should be even or odd. And that's the way they are defined. So they are odd symmetric or even symmetric. And you can see it here. Now the point is that, so all of these filters will give you the linear phase shift. For sure, the linear phase shift. Now let me explain it with okay, I can go to the window, the last method. So these are the structures. Let me explain and then we can go to the MATLAB. It's just the final slides. It's we can just skip too many of them. So we have these 4 structures for the FIR filter. Now you want to design the FIR filter. Which of the methods you want to use now depends on those 3 methods that I explained. So this, you want to have a low pass, high pass, or band stop filter based on one of these methods, type 1, 2, 3, or 4. So here, you know, it's a second layer of filter design that you didn't have such kind of layer in the IIR implementation. But we have to already know that one of these methods, for example, type 1, is something that you can use for the low pass filters, also for the high pass filters. But for example, type 2 is something that you can never use it for the high pass filters, for the low pass filters, because of adding a 0 in the lower frequencies, or type 3 for the high pass filters, or type 4. So you have to somehow come up with the type of the filter based on the application that you need. But the computer will actually, the FDA tool, it actually does it for you automatically. You don't need to think about the type of filter that you want to use. It automatically does it. One of the other approaches for designing the FIR filter was using the windowing method, and it's just it's very quite similar to what we had the idea of impulse invariance. We just take one of the windows and take the samples out of that. So any of these windows will give you a kind of, so you have the h of d, which is this window times the ideal filter that you need. So you have an ideal filter, low pass filter, you design it, you have it, you set it up, then you say, okay, what kind of window I have to multiply by that ideal filter to get the FIR filter as an equivalent in the output. And these are the types of the windows that you can have. But let me go through the software to see exactly what happens. So you use fdatool. So in MATLAB, you just write down fdatool. The result would be this graphical user interface program that's written in MATLAB. So, for example, you need to design a low-pass filter. So you just select the low-pass filter. And let's first start with the IIR filter. Then for the IIR case, you use the Chebyshev elliptic or any other cases. So we can have Butterworth, the maximally flat one. Then you can specify the order, or you can ask the software to choose the minimum possible order. Depends on you. If you have a kind of limitation for the order, you can manually set it. And for example, you can here say that these are the extra settings that you want to match exactly in the stop band or in the pass band. Which one? For example, you say that for me, the pass band is really necessary to completely match. Then the specifications for the frequency. So the unit is hertz here. You have the sampling rate of 48,000. And for example, if you're in a project with 16 kilohertz, you can just use the 16 kilohertz. The passband frequency here is, well, we can use it for the speech setting, so we use it 3.4 kilohertz, and the stop band to be, for example, 4 kilohertz. And for the gain in the magnitude specification, we can say that, okay, the decibel, we want this passband to be in a gain 1 and 80 dB attenuation in the stop band. Let's see if it can design it. So it got the order of 42, so it's too much. 42 is really a large order. And here you see that this is the maximally flat. 3.4 kilohertz is the frequency of pass band, and afterwards it starts to actually attenuate it. And we see that it actually has problem with the stop band. It couldn't actually match with the stop band. So if we change it from the passband to the stop band, let's see the design of the filter, how it changes. It says it's done, but it's not doing. Okay, let's have a FIR filter design. For the FIR filter, we can select the method of windowing, or we can use the other methods that we already had. So, for example, we use the windowing method, the one that I just explained this in the final slides. You can take the window to be anything. So we can have the Kaiser window, or we can rectangular window, Bartlett window, which is the triangular window. Hamming or Hanning. Hamming is the most prevalent one in the speech case or the audio case. So we use the Hamming window. You can specify the order. We can use the minimum possible order. And let's have the same sampling frequency and to see what happens. So this is the Hamming result. First of all, we have to know that when you design a filter, the response of the filter in digital case is the frequency response is actually periodic. So if you use the MATLAB if you write down everything by yourself in MATLAB, the figure that you see is a periodic form. You just take the first period. But here is already mentioned. It's already the first period is written. The point is that if you use the FIR filter, so you see that here, for example, with order 10, it's not that much sharp. It's passing from these frequencies is actually started to attenuate it, and here where the attenuation goes to almost minus 70 dB, but then again starts to increase. And you can have different types of, this is the smooth one, but if you use, for example, a rectangular one, then you will have definitely a lot of fluctuations. These side lobes, which were because of that Gibbs phenomenon. So let's have it with, you see here. So you have these fluctuations. This is the gain in the passband. But here you see these are the fluctuations because of the Gibbs phenomenon. You'll see such a kind of thing. So normally it's not a good window. The rectangular one is not a good window because of these lobes that you see. So these are meaning that these frequencies will pass through the signal. And any frequency that is located here, here, or here in the maximum gain, they will pass through the signal with some attenuation. But for example, Hamming and Hanning, they are really good windows. They are smoother and they have side lobes, but the degree of side lobe, you see that is almost, with respect to the main one, is 20 dB lower. So it actually, the ratio between the side lobe and the main lobe is too much, and it's good enough. So it's smoother. And in the time domain, the Hamming window looks like this. The Hanning window looks like this. But for example, the rectangular one is just rectangular. So time domain, you're considering all the taps of the signal, all the elements of the signal in the same way. But when we are using, the idea is that if you're using a smooth window, then it means, in reality, it means that there are some samples in the time domain that are more important than the other samples besides, the samples in the neighboring. So you give different weights. For some samples you give higher weight, for some samples you give lower weight. And that makes sense, specifically when you are doing the overlap of the windows. So we're not taking the window instantly and then just jumping to the next window. Normally, every window has some overlap with the other, and at least it has 50% of overlapping. So it means that just some of the samples are really important. These are just belonging to this window, but for the rest of the samples, they will be also considered in the next processing window. That's why the Hamming window makes it smoother in the time domain. As a result of that, it will get a better quality for the filter in the frequency domain. The ratio between the main and the side lobes increases a lot, 25 dB a year, and it's worth for that. But we know that already these are the overlapping windows that should happen in the time domain. For the rectangular one, it considers all with the same weight. As a result, we have a side lobe which is really high with respect to the main lobe. And that's how it's actually designed. So we don't need actually to go further, because here we have it, and you can easily just store the filter results. So you can give a name, and for example, if this is the name, and then you can easily go to that filter text script, and then you can see that how much is the filter taps that you have to assign for that. So these are very basic things about the fdatool, and time is already past too much. So in the afternoon we'll have more just filling out the gaps that we had in the theory, in the basic DSP theory. There are a lot of things I mentioned, and I'm now insisting that there are a lot of small things of the theory remained, but we don't need it in practice. We don't need it to go through that. For practical cases, the amount of DSP basic theories that we said is enough, but again, this is something that just useful for the rest of the theory, the class that we are going to talk about, because we have no deterministic signal in practice. So just we got the theory, and we will go to the next topic. And probably in the afternoon I will do some MATLAB examples also in the class. And I'll also try afterwards probably to upload some homeworks, both paper-based homework and MATLAB example for the homework. Any questions? Okay. Thank you so much.